Hello everyone, thanks for being here over lunch break. So my name is Cyrus. I work for the developer advocate team as a specialist. In the past 6.5 years in AWS, I have been in different places, most of it in the AWS AI and the SageMaker team. So, but not now. So I have with me Susan. She's a research scientist from transportation, right? From the transportation, I've supported them on a project that she has been leading, using explainability on basically the NLP project. So what I'm going to do here, I'm going to go through some basic definitions and what explainability is. Then I'm going to hand over to Susan that is going to get you through basically some general strategies for perturbation when it comes to natural language processing. And then she gives you a project report, and then I will give you an update on what Amazon SageMaker Clarify is providing you out of the box for your models for explainability. So first, why should we care? So let's see what it is first. So there are two types of explainability you can have on a model, right? So one is you explain the principles under which a model makes a decision. So why do you generally make this decision rather than that type of decision? The other one is local explainability, when you explain something, a single decision. Like, for instance, you go and say your loan application has been rejected. You are entitled to know why that loan application was rejected. The rules in Europe, for instance, if somebody basically rejects your job application, you have a right to request, why did you reject me? So if a human does that, human has to be able to explain it. If a machine does that, you have to explain why the machine did that. So what we have here in the context that we have is about local explanation. So let's see how it works. So you've got a loan application, you put your loan application in, and an online system immediately tells you, nope. So then you're going to file a ticket or make a phone call to a human being and say, why did you reject my application? They're going to look at some sort of an explainability, basically, method they're using, and they're going to explain to you that it was because, let's say, this value was given to your income, this value was given to your, basically this weight was given to your, basically, total debt, and the combination of those brought the machine to the decision that this no was much stronger than the yes. So that's something without ambiguity that tells you exactly what feature we used. And then what's the benefit of doing that? So first thing is trust, right? So there were a couple of studies back in basically late 2000s in two different countries. One of the countries, if you had a name that was hard to pronounce, and especially if it was an ethnic name, you would have 54% less chance of being invited to a job interview. There was a different city in Europe that on the top of your name, your postal code was a discrimination factor. So what happens here, then, even if you're rejected for good reasons, then you think there is always something malignant, there's some malice in the system. You don't trust it. So same goes with the machine. So if the machine is going to make the decisions that you cannot trust, you always think there is something fishy, therefore, we want to build trust with the system, so we have to be able to explain why a machine makes a decision. The second is transparency, goes hand in hand with trust. If transparently you know why you were rejected, so you no longer think the system is basically doing something against you. Then there's fairness, there's bias, let's say, goes again hand in hand. So the bias is, if you're from the suburbs of Paris, you're not going to be invited to a job interview, but if you have a postcode that is in basically central Paris, then you're going to be invited to an interview. So that transparency, that fairness is going to remove that. So they're all connected to one another. Then there is accountability. Let's say you have a trading organization. I'll give you an exact example. When in Europe, the energy industry became privatized, so these old government companies, they end up having control over production, distribution, and trading. So there was regulation that you have to explain your trading decisions, and if you cannot explain your trading decisions, you're going to get hefty fines. There was one major company in Europe, they could not explain their trading decisions. They were given 5 billion euros worth of penalty, and then they settled it with selling their distribution network on the top of basically within a space of time building a database to explain. So now the machine makes those decisions, you have to be able to comply with those regulations. Troubleshooting, which is close to what we're doing here, because the project that we did was triggered by troubleshooting to do explainability. You want to see your model is behaving badly, erratically, it's just not performing. You've got to take a look inside it to see how it makes decisions. Oh, that's right, it shouldn't be doing this and this and that. So you can actually deal with your data, deal with your method, and basically improve your model. Sometimes the goal is that a model should be outperforming humans in the similar task. So if a model is consistently outperforming humans by a large margin, it makes sense to take a look inside of it and tell the human this is the way decisions are made. So in order to create this mutually reinforcing improvement in both machine and human decision. So where's the history of this thing? It's hot now, everybody's talking about it, but it's got a very long history. Very, very long history. I remember back in the Stone Age, when I was at grad school, that nobody wanted to talk to us except for philosophers. So they were keep talking to us about in the philosophy of science. The level of detail has to have some relationship with what's being explained, right? So let's look at the example that we have in here. If we look at the subatomic particles, like the neutrons and protons and that sort of thing, all the neutrons have the same weight. They're all neutral, and they have no charge. The size is the same. Protons are the same. Electrons are the same. So they don't really explain the behavior of water at the boiling point, at the freezing point. It's just too detailed. The level of detail doesn't have constituency relationship with what's being explained when we are talking about the boiling point of the water, expansion, contraction. But when you look at the molecular level, that is a good level of basic explanation. The same goes with basically neurobiology. If you're trying to explain why I made this decision or that, why I made basically this sentence rather than that, so you cannot explain it on the basis of the agitation of my neurons. You need something at a little higher level that has constituency information. Same goes with the neural networks. When you look at it in here, on the left side, you see a text generator, tiny little network, got 3 layers. It's got an embedding layer, it's got a gated recurrent unit layer, and it's got a decision layer based on basically a dense MLP. So that little tiny network has got over 4 million parameters, and I have taken, basically on the right side, visualized the values of the values of the hidden units. And it makes no sense at all in terms of why did you make this sentence rather than that sentence? Why did you make this word rather than that word? That doesn't explain anything. It might explain that the distribution of the weights is not good, you know, that sort of thing, but it doesn't explain what's being done by the network. What level, the correct level of explanation, is what we have in here. Something that explains the sentence. So these two sentences is the same sentence parsed 2 different ways. I shot the elephant in my pajamas. So it can have 2 meanings depending on how you parse it. One side says, I shot an elephant while I was in my pajamas. The other one is, I shot the elephant that was in my pajamas. That basically means you shot yourself in the leg or hand or something. So that is the correct level of explanation. The reason I'm setting that up, because there is some concept when we say in AI explainability, it needs to be human understandable and it needs to be intuitive. And that is not a, precise definition, so we're trying to build up that thing, what it means to be intuitive and human understandable. So now, let's get to see how it works. Set the context. The way the models that we're talking about are basically called the surrogate model. A surrogate model is a simple model that that explains the behavior of a more complicated model. Let's say a linear model is understandable. A neural network is not understandable. If we can create a linear model that explains the local behavior, local decision, and that's something you can rely on for explainability. Not every explainability model is perturbation-based. What we do here is perturbation. So perturbation is making changes in the input and see what happens to the output. Then you can see what's important. I give you an example. A facial recognition system is going to chunk my face into different segments, and then is going to be a little bit of a bridge of the nose, a bit of the left eye, and then at the end is going to say, oh, that was basically the eyes and the bridge of the nose was the most important segment of this face. So you can randomly create the superpixels, and those superpixels, you can turn them off and on and see which one has the most important, basically, which feature can be attributed the most important probability for making that decision, which brings us to the next line, which is these are feature attribution based. We're looking at the basically input and see which feature is the most important, or which cluster of features rather. It's about local explainability, explaining single decisions. It's a black box approach, so it's model agnostic. We don't care what's in the model, but the model has an input and an output, and it's post hoc, so the explainability is not built inside the model, is built on the top of that based on understanding of its inputs and outputs. So what is a good So in this context, the context of perturbation-based, local explainability, black box, model agnostic, and all of that, what would be a good characteristic for an explanation? So it has high local fidelity. It's got an equation, but forget about that to see what it is. The closer, the surrogate model to the original model, the better it is. So in these two examples, you see, let's imagine the orange graph being the model and the blue graph being the explainability. You see one of them has twice as much error compared to the other one. The high local fidelity, is the one when those basically distances are closer. It's not the average distance because we're talking about the local explanation, so that means at a very local point, at a single local point that you're making explanation, it has to be closest. It has to be intuitive, so it has to be something we understand, like structure of language, as opposed to a bunch of basically values that you can put on graphics, and it has to be model agnostic. On the right side, you can see what we have is two different object detection models. To both of them, I have applied LIME. So they're pretty much both of them looking at the same sort of regions, even though the models that are used are completely different. One of them is ResNet 152. The other one is Inception v3. So completely different model, completely different architectures, but when you apply the explainability to the black box model, there are basically similarities in the regions that are selected. So it tells us that it is basically model agnostic. So we take a look at two models very quickly. First one is LIME. So LIME came, I think, about 2016. That's a perturbation-based model. So the idea is, if you explain a local explanation, and we make that local explanation basically in a small enough neighborhood, then we can approximate that neighborhood to a linear system. It is akin to, when you're trying to do Newtonian physics. So if you're looking at a small enough, basically, distance, they can ignore the curvature of the Earth. But if you go further, so how does that thing goes? Yeah, I think I fired that thing. So this is basically, it's a very famous example. It's called Newton's cannon. So what it does, if the ball lands near your feet, what you can do, you can apply the geometry, the Euclidean geometry, and you can basically ignore that the Earth has curvature. But if you do basically throw the ball so far, far, far away, it starts going around the Earth, and then the curvature of the Earth could no longer be ignored. So the idea behind LIME is to create a neighborhood, is to create basically around the point that is explained, that is small enough that a linear model can explain what happens. And linear models are quite understandable because there is nothing complex in y equals 2x plus 1. There are no hidden values, there are no mesh of neurons, there are none of those nonsense. So what you have is a linear model that explains basically the original model. So, and it's used for local explainability. So something a little closer, this is from the original paper. So what you see that the perturbation is, you perturb the original image by chunking it into superpixels, and then that creates a new data set for you. And then what you do, when you turn on and off these superpixels, you basically give that to the original model, and it gives you a probability output when you see 85% or 52% or whatever. And then you can use that. You can basically, when you get a proper local neighborhood, then you can actually approximate that into a loop, into a, oh, by the way, those percentages are used as the label for a new data set. And then you can actually create a linear model that in this case tells you that superpixel is what's the most important bit that tells you about the frog being a tree frog. So there are issues here. And the issues are there are two hyperparameters in SHAP, in Lime that are more art than science. You got to play around with it until it happens. One is the width of the kernel. The other one, it uses basically kernel methods to reduce dimensionality. And there is basically width of the kernel, and there's something else that are very difficult to figure out. Then comes SHAP. What SHAP does is trying to use basically, let's get to kernel SHAP at the end. Let's continue with the process. So the SHAP is based on a game theory called the n-person games. So what you have, let's imagine a football team. You probably call it soccer here. So a football team, there are 11 players on the field. They all contribute for somebody to score. And then you want to distribute bonuses. How do you give bonuses? Do you give it all to the person who scored the goal? How about all those people in the midfield that did the hard work of maintaining the game for a person to have a glorious moment? So in an n-person game, when the whole team is trying to contribute to an output, and yet they're all competing over how much reward they're going to get. So basically Lloyd Shapley created something in game theory that's called Shapley values that provides you a unique solution to an equation that fairly distributes reward to effort. So if you take that into machine learning, it becomes a payout function that assigns reward to the feature, basically to the superpixel features. That's the same thing. All of these superpixels contribute to the output, but how much? So you can actually, unlike Lime, when you had to do lots of magic in order to figure out the hyperparameters, so you can do something with Shapley, so you can actually solve an equation that has a unique solution. So there is no ambiguity here, and that's a good thing about it. One of the most implemented types of SHAP is kernel SHAP, and the kernel SHAP is using Lime's kernel trick and creating certain structure that you get into that SHAP equation and solve it. You have SHAP values, so you have unique values. So let's try to see how it works in example. That's another example. A team of salespeople. There's a salesperson, there's a solutions architect, there's a technical account manager. They go into an account. If the salesman goes alone, makes 100K, solutions architect makes 80, the technical account manager makes 65K. If you create coalition of two of them, A and B, they make 160, which is less than 180, so it's not a good coalition. So that coalition needs to work on its teamwork. So, and then you have AC makes 140, still not a good coalition. BC together makes 100. And the grand coalition makes it 250, which is more than the total contribution of each one of them. So the point is, if you want to decide how to give commission to these people in the sales team, how would you go about it in order to be fair to them and encourage them? So one solution is just give them equal amounts. Well, it's not fair, is it? So the person who makes 100, expects to have more commission than the one that makes 65. Or the other one is take the individual contribution, divide it in the total, basically, value of sales, but that doesn't encourage teamwork. That means it's all about your personal, basically, personal performance. So, and that we're going to use, sorry, Lloyd Shapley, because of copyright reason, I had to remove his face. You can Google it for yourself. So And so the one that was in the open, it was him before dying, and I didn't want to put it here. So, but I think he's still alive, so I hope he is. So, but he basically introduced that Shapley values back in 52, and in 2012 got the Nobel Prize for it, and it's become one of the most prominent ways of doing feature attribution in machine learning by giving how much reward you have to give to basically inputs. So here, if you're a simplified version of that, if A makes 100K, B makes 40K, and the total is a good coalition, a grand coalition of 140, is it 140? No, 160, so that's a super additive system. So what you end up with, if you apply Shapley method in that, so then you end up having basically 150, that would be the unique solution to that problem. It's been implemented for basically doing machine learning through a library called SHAP, and that SHAP in here, you can see that. That's a loan application. Sorry, that's not a loan application. That's a sentiment analysis I've basically run in here. So the first time it says it's a wonderful waste of time in an IMDb data set, if let's say there is a sentiment. So a wonderful waste of time. It does positive and it does negative, and it just gives you a number, that the number is that 0.9, whatever you see in here. In the second example, I have done, it's a wonder fill. I have a typo. Basically, it's a wonder fill waste of time, and you expect the system to be able to deal with those sorts of things. And it doesn't. So wonder fill, it's going to get inflection. It gets wonder, so the numbers change. That basically the positive negative changes. So that means it's using it naively out of the box is going to be tripped by things like typos and synonyms and all of that. And that brings us to the next basically segment of this talk, which is about perturbation strategies, because we applied not SHAP, but we applied explainability onto the project that Susan is going to explain to you, and then is going to see how you got to be doing this creative work of dealing with basically perturbation of the input in natural language processing, with typos, with synonyms, omitting the words, and that sort of stuff. And with that, I want to invite Susan to come up here and take over.
Strategies that we can use in order to have some explainability. And let me now walk you through what perturbation means. Sorry. Yes. So what is perturbation? So perturbation was first raised by the work of Taylor and Cyrus, who worked on the perturbation of certain images where they applied certain gray masks on the images, and so what this gave as an output. So what Cyrus was describing before is this image of a face that can help us make face recognition. So what we can do is start applying some gray masks on certain places of the face and see how this would impact an output of a black box model. And through these types of perturbations, we can end up having a certain explainability of black box models, like those that we use in NLP and that have state-of-the-art accuracies, but are deep learning based, and then there are black box models. So let me walk you through the image that explains a bit what perturbation is about. We can have a very tidy input where nothing is changed, and then we give it to a black box model that would give us a certain output. But we don't understand the process behind. How could we get this output from this black box model? What is the decision-making framework that led us to that? Now, the idea of perturbation is impacting a little bit of this message or part of this message and making it a noisy message, and then giving it to the same black box model and getting the new output. The idea is to observe the differences between the two cases where we had the original input, which was not perturbated at all, and then with the new output where we perturbated part of it. And this would give us an idea of the importance of this part we perturbated on producing the output, and then help us understand better the black box models. So now I'm going to give you some examples of how perturbation was applied to different types of data in literature. The first one is on images, where we can apply the so-called occlusion. So the idea of occlusion is making some gray masks on certain parts of the image and then observing the difference in the output. And in this way, we would understand how every part of the input is important in defining the final output. Another example is what Cyrus has talked about on Lime, which is a local perturbation in order to have interpretability of models, to using some simpler types of models, like linear ones, which can help us as well approximate certain black box models on local basis. There are also videos where we can actually apply perturbations through temporal masks. How can we perturbate videos? We can flip the images, we can make a freeze on certain parts of the video, and then we start measuring the impact on the output and comparing it to the output we have if we did not apply any perturbation. We have it as well for reinforcement learning entities, where we can start perturbation the rewards of these reinforcement learning entities and try to understand how they work. Now, how can we then produce the results of perturbation? We can apply the so-called saliency maps, and the saliency maps will try to let us understand the importance of every part of the input and its impacts on every part of the output. Let's look at the first image. We have an image of a 9 in a certain entity recognition part, where we try to recognize the number that is on the picture. So we see that the place in the bottom of the picture, if we perturbate it, then this has a big impact on the output, because it makes the 9 look like a 2, and then it changes the process of the algorithm. And so we start understanding from the map which parts of this image were important in defining the recognition of the numbers. The second example is a translation example. And here, we are mapping every word from the input to every word in the output in the so-called attention-based models. So attention-based models are actually models that take into consideration the context in order to try to give a certain output. And these are basically used in natural language processing, like the one we have here for translation from English to French. And then the word good in English can have both translations of either bon if it is a man or bonne if it is a woman. So these are two different translations. And the way we are computing this is looking at the context in order to try to have an idea of the good translation to make. And this is another way we can represent the impact of every part of the input and its impacts on the output. And we can use perturbation-based methods to help us understand how every input is related to every part of the output. Then there is a question, how can we perturbate texts? And this is basically related to the projects that I will be talking about after that. So let's talk about some types of drastic perturbations of text. We can have the naive approach, which is also the most neutral one in perturbating text, where we will just start masking certain words in the text. For example, here I have, when life gives you lemons, make lemonade. So here we see that we are masking word by word the words that are in this idiom, and then what we can do is simply giving it to a black box model and seeing how the input would react to these changes or to these maskings of words. This can also be deleting the word altogether. We have another example. If we are to teach peace in this word, and if we are to carry on the word against war, we shall teach it to the children. So here we see that we are masking word by word. And the idea is reapplying again and again the black box model to these new outputs which are perturbated and observe the final impact. Let's move to another one. We can also have character substitution. So the idea of character substitution is that we are replacing certain letters in the first text by random letters or by keyboard errors, for example. We can use for that some already existing libraries like the NLP OG library, which can help us make some changes to the text. So here's the text we have. You must be the change you wish to see in the word. And you see that some letters are randomly changed, which would produce new words. And you can even direct these types of errors through, for example, keyboard errors, and mimicate the keyboard errors and see what the impact would be on the output. Then let's move to some gradual perturbations. So here we are not talking about drastic ones where we are deleting words, masking them, changing them to unknown words. We are talking about slighter changes. For example, replacing by a synonym in the first case. So here, for example, an apple a day keeps the doctor away could be turned to an apple a day keeps the doctor by, Or an apple, a 24-hour interval, keeps the doctor away. So here we are churning certain words in the first input to something like a synonym, but it is not really changing the whole sentence. We can also have paraphrases, like you must be the change you wish to see in the world, or can be turned as you see it to your experience must be the change you wish to actually see in the spirit world, for example. And this is a slight paraphrase of the text where we're trying to keep the meaning, but we change a little bit the wording. So what are the pitfalls of perturbations? We have basically two main limits in literature. The first one is going to out of distribution. What out of distribution means is what is actually portrayed in the picture, where we are moving from one planet to totally another planet. So for example, we are talking about climate change, and then we end up talking about software engineering or about Intel. And this makes us really move from one word to another, and then the model is no longer able to really interpret and take the perturbated text, because now it's no longer perturbated only, but it's very perturbated, and then we are out of distribution. The second thing is, now if you are making very slight perturbations, like replacing a word by synonym, that will not really impact the meaning. In that case, we have also this question of interpretability versus robustness. What we would be measuring is not really the importance of the wordings, but maybe just the robustness of the model that we are using. Now let me talk to you about the project report from Amazon Transportation, where we applied perturbations to sentences. So basically, the project that we have experienced is the so-called on-call assistant. So let me walk you rapidly through the story behind it. So in Amazon, we have many products, like scheduling algorithms or products for optimization. And then people start using it from the business, but they can end up having some bugs, some problems in these systems. And in these cases, what they would do is raising a ticket. So a ticket is basically a description of a problem that they are facing, that they would raise, send it to the engineers. Engineers would then look at this ticket, analyze it, find out the root cause, and then solve it. And then the business can finally use the model as he used to. Now, what we suggested in this context is that we may have some repetitive types of problems. So a problem that occurs now may have occurred in the past, but the thing is that engineers are always diving deep in every separate ticket without taking into consideration the knowledge we have from the past. So the idea is that when people are closing tickets, they can just talk about the root cause in the comments or in certain sections in the ticket, talk about the solution that they found out, and then have this documentation as historical knowledge. Now, the objective of the on-call assistant is given a certain new open ticket that needs to be resolved, and given the historical closed tickets, which is our basis of knowledge, we are going to produce some recommendations which are the nearest neighbors from the past, which means the tickets that were the most similar from the past. And from this, engineers can have access to the knowledge of root causes, solution that they used in the past, and then be able to rapidly close the ticket. The idea behind this is that we also want to automate some problems. If they are repeated again and again, the solution is the same, why not to just automate it and then save time? For that, we used the so-called black box models. Basically, in our case, we used one model that was the BERT encoding model, which is an attention-based model, and which is very littly explained. So what we did is that we started from the BERT pre-trained model, and then we took the encoded layers of this pre-trained model. And the idea from that is that we are turning every text or every description into a vector. This vector will come from wording encoding. So what BERT does specifically is encoding every word, and it puts it in a dimension of 12 to 768. This dimension is a dimension for every word. Now, the 12 that we have here is the number of layers that the algorithm is given. We are going to take the last layer or the previous to last layer and then have a vector of 768 for every word. In order to have a representation of a text, we just average over the words. And this will give us, for every text or for every description, a certain vector of 768 dimensions. Then, we would just apply a distance-based model. We can use the ball tree model that would try to look for very near neighbors of this ticket. So the ticket now is no longer a description or a text, it is a vector. And then from this vector, we are going to look to the nearest neighbors. But the problem is we don't know how from a text we ended up having a certain vector and not another. This is a black box part of it. And if we were to automate certain tasks, if we were to suggest good solutions, we need to understand the decision-based processing. This is very important as well because we are in the so-called unsupervised tasks. So we don't have clear measures of accuracies because we are not looking for a certain label through the model. We are looking for nearby vectors. It's just like what we do when we do clustering. We are looking for nearby vectors. And so we need a certain metric of accuracy. But we don't have it because it is nearby vectors. We can have some accuracies of clustering resolvation, these types of things, but we cannot have clear accuracy measures. And this is why we needed an explainability model. So as I explained to you, the challenges were lack of quantitative metrics to estimate accuracy, which was very painful because we cannot automate if we don't understand. Then we have consistent requests from the business as well to try to understand better our model and how from these texts I ended up having these nearest neighbors. Now the goal for the perturbation-based explainability is actually to improve the model, to be able to troubleshoot it and see when it is not working very well, and also be able to provide the required interpretability to our business. How does the perturbation model work? So we start from a new open ticket. And for this new open ticket, we can get the on-call assistant. So what we do first is we give it to the on-call assistant. We get the outputs that we get if you have not perturbated anything, if you have the original text. And this is the first line that you see where we get the 3 green outputs. Then what we do is dividing this same ticket into sentences. Let's imagine that our text has 25 sentences. We will be dividing it into these 25 sentences. We would take one sentence first. This sentence, let's say sentence 1, would go to a perturbator. What the perturbator would do is doing exactly what we have described, making perturbations. We decide whether they are drastic or gradual. And then it would give us a perturbated sentence number 1. What we do then is just concatenating this perturbated sentence number 1 with the rest of sentences that were not perturbated. Okay? Now we get a perturbated text number 1, where the only perturbated sentence is the first one, and all the others are not perturbated. They are as original. We give it to the on-call assistant. We have 3 nearest neighbors. These may be different from the previous ones. Okay? What we would do next is comparing, observing the differences we see. So comparing the results that we get, if we have not perturbated anything, with the results that we get when we have only perturbated first sentence. And then we would define just a metric of changes we have observed. The changes may be, what is the number of nearest neighbors that changed after we applied this perturbation? Or what is the distance to previous nearest neighbors when we have not applied perturbation? So we will define a metric that would give us a certain perturbation impact in terms of difference that it made to the output. Now, what we do is reiterating. So we have our ticket. We have different sentences. We would give them to the perturbation algorithm, and we would be measuring in a loop the perturbation impact for every one of the sentences. Then we would link this impact to the importance. If the impact is big when we have removed a certain sentence, then it means that this certain sentence is important to the output as compared to another one that did not make any impact when we removed it or when we perturbated it. Let me give you an example. This is an example of a ticket that we may have. So the ticket starts with one sentence. What is happening? And there is a description of the problem that is related to a certain Pentax tool in Amazon. And then we have a final sentence, expect an answer from engineering tool within 2 business days. Now let's look at the nearest neighbors. We see that the nearest neighbors, or the 3 nearest neighbors, are all beginning with the same sentence. What is happening? Finishing with the same sentence, expect an answer in 2 business days. And then the core information in every one of these tickets is different from the core information from the previous ticket. This we would portray in the importance graph, where we see that the first sentence and the fourth sentence were important in defining the nearest neighbors. In this case, this is a problem. This is an example of troubleshooting. The algorithm was not looking at the right information. It was looking at a repetitive sentence, expect a behavior, or what is happening. So this is not any important to the solution, right? Now what we would do is solving this. We can remove these sentences from all the text and then push the model to focus more on the most important information. And this is a practical example of how we can use the perturbation-based algorithm. Now, we have also compared the different approaches we had in perturbation. We said that there are different approaches to perturbation, some of which are drastic, some of which are gradual. Then we see that when we are applying drastic changes in perturbation, these have some similar results. Mainly, there is the naivest-like approach of just removing, for example, and there is this character strategy which would drop certain random words in the text. And then the results we get here are different from the ones we get if you just apply gradual changes, like replacing a word by its synonym, or replacing a certain sentence by its paraphrase. And this is very important, because we need to make sure as well that when we are changing slight words, making synonyms, they should not impact a lot the solution we are getting. We should not get something very different because they just use a certain synonym instead of another word. So our suggestion is that the drastic methods should be used in importance, measurement, or interpretability, while gradual ones should be used for robustness. When we apply certain perturbations that are gradual, we do not need to find a lot of impact on the output. So in our case, we went for removal strategy in order to estimate interpretability and synonym strategy to estimate the robustness of the model. Now, let's rapidly talk about the outcomes and practical tips we get from this. So, thanks to this perturbation model, we succeeded troubleshooting the model scene where it was not relying on the right information. I gave you an example of discovering unimportant sentences which were counted as being important by the algorithm in order to define the nearest neighbors. We also could provide some explainability to our business stakeholders on the results they are getting and the solutions they are getting in order to understand if the core problem was tackled in providing the recommendations. Now, the technical tips is perturbation methods can be generalizable to all deep learning methods. So as you see, the methods we applied were model agnostic, so they can be applied to any type of attention-based model, black box model, and then we can just start using the same algorithm. Then we would recommend for explainability some drastic changes, like removal to be very objective and not to be making some synonyms or slight changes, and for robustness, use some gradual changes in explainability. Now, we also combine this with some embedded layers analysis, where what we can do is looking at the internal neural learning of the model, and then we start perturbating the internal layers in the model through adding some noise and see what the impact is. This would be more important in order to understand how the model is learning, and can be practically important to transfer learning from machines to humans. Now, I will let you, Cyrus, talk about the Amazon SageMaker in explainability.
Right, bread and butter. So, we created Amazon SageMaker Clarify that does explainability, predominantly on the basis of SHAP, and a lot of kernel basically SHAP on that it does. So generally, it provides both local and global explainability. It detects data biases. That is very important. Your data could be biased intentionally, unintentionally, accidentally, but your model as good as your data. If your data is biased, you train a model that is biased and is going to basically spit out biased outcome. And it also detects bias in trained models. So it could be not just the data, the model could be trained because you have the labels, and the labels are based on historical information, and people in the past could have been biased towards this thing or that, and then they might have, because of your basically labels, you might end up with bias and basically skewed towards basically, I don't know, rejecting certain people's loans. So it actually detects and gives you warnings. And more importantly, it monitors your model over time. So if patterns are emerging that something is getting biased in there, then it's going to actually give you warning and scream at you until you fix it. So global explainability, that's an example it does. So it's basically, as you see, is feature attribution. It's trying to show those features and say which feature is the most important one. And then if you see there is some sort of a bias is happening in there, is going to basically give you warning about it. So it's the whole model thing. You can take a look at it. Sorry, there's no warning here. And it looks at your data bias. It analyzes your data and says, you're skewed towards this field or that field. So there's something, you might come up and apply things like downsampling. You might do something else. You might do something that your data would no longer carry the bias in it. So it does model bias. So it basically checks your train model. So let's say on regular basis, you are going to reject job application of people with some sort of basically postal code that you don't like. So how does that come to your model? Previously, your data set is coming from decisions was made in the past, and that bias of the humans who are sitting and looking at those codes, the postal codes, are going to seep into the training of your model through your labels. So it actually tries to take a look at that instead. And it tells you you're biased towards, basically your model is biased towards postcode. And to be honest with you, you might want to remove that postcode from your data in the first place, or just do your model do differently because postcode is important because you want to reduce the amount of commutes people do. So that would be a different reason for that. So, and it monitors things over time for bias. Let's see what happens. Real world changes. Let's say people move to a different neighborhood that they could barely afford to some edge of it, and the property price goes down, and then people who were not entitled to get a loan, they're suddenly entitled to get a loan, the ones on the margins of the income that they could not get it before. As the real world changes, new bias might basically creep into your model, because based on the previous reality, it wasn't biased, but the new reality starts unfairly punishing one group of people over the other. So that is giving you warning over the course of time as it continues to try to look at your model. Is integrated with all of these basically warning systems we have in AWS infrastructure. So the same thing is going to tell you what happens. So that was the behavior of the model. And that is it for us.